Hey, welcome back to Combinatorics. In this video, we're going to start discussing induction. More specifically, we're only going to focus on the type of induction that is called weak induction. Before we get to any induction though, let's recap where we were at in the previous videos and see how it relates to induction. In the last video, we started discussing the inclusion-exclusion principle. This is a principle that helps us determine the cardinalities of sets. We proved the inclusion-exclusion principle when we had 2 or 3 sets, but the principle is much more general than that, and it can be applied to any number of sets. When we have at least 4 sets, we still need to prove the inclusion-exclusion principle. But the method that we'll use to prove it will be very similar to the method that we used for n equals 2 and for n equals 3. In order to prove this principle more generally, it will be helpful for us to introduce a new tool that we'll use a lot of times in the course for many different proofs. This tool, as you can probably guess, is induction. And like I said earlier, we'll be focusing on a specific kind of induction today. But in later videos, we'll be discussing another kind of induction called strong induction. So let's get to weak induction. So for weak induction, we have some property P, and P can be any property of the natural numbers. For example, P of n could be the proposition n is divisible by 1. Induction consists of multiple axioms of arithmetic. So for any proposition that you have that takes a natural number and is either true or false, you can define an induction axiom. And the induction axiom will look like this for whatever proposition P that you're considering. So the axiom says that if we have P of 0 true, and if we can show for all n that P of n implies P of n plus 1, then we can conclude that for all n, P of n is true. I want to note here that the quantifiers in this axiom, the for all n's, they range over the natural numbers, and the natural numbers are the integers starting at 0, and then going 1, 2, 3, and all of the other positive integers. So we start at 0 instead of at 1. And with this induction axiom, we can think about it, visualizing it in terms of dominoes. So say we have a bunch of dominoes. We can knock over the first domino, and that domino, if we arrange our dominoes right, will knock over the second one. And the way that the first domino knocks over the second one, that same way that we arranged the first one with respect to the second one, we can arrange the second one with respect to the third one that way too. So the second one will knock over the third one, the same way that the first one knocked over the second one. And the third one will knock over the fourth one, the same way that the second one knocked over the third one. It'll just continue like that. And that's the way that we can think about weak induction. is that we prove some base case. We show that P of 0 is true. That's when we knock over the first domino. And that's this part right here, the P of 0. And then we prove an inductive step. So we assume that P of n is true. And we use that to show that P of n plus 1 is true. And if we can prove the base case and the inductive step for P, then we can conclude that P is true for all the natural numbers. And again, the natural numbers, we're assuming that they start at 0. Now, for some proofs, we won't necessarily want to start at 0. Instead, we'll prefer to start at some positive integer and say that it's true for all positive integers that are at least the one that we started at. And we can define an induction axiom for that case as well. And all that axiom will say is that if P of k is true, and if for all natural numbers n greater than or equal to k, we have P of n implies P of n plus 1, then we can conclude that for all n greater than or equal to k, we have P of n. So this axiom here is pretty much the same idea with the dominoes. We have a bunch of dominoes here. But now, instead of flicking over the first domino, I'm just going to flick over the fourth one, let's say, if we're doing k equals 4. And now the fourth one will knock over the fifth one. And we'll position the fifth one so that it knocks over the sixth one the same way that the fourth one knocked over the fifth one, and so on. So the first few dominoes over here, it doesn't really matter how we arrange them. We're not proving anything about them. All we care about is the dominoes at the fourth one and past that. So 4, 5, 6, and so on. And we're able to conclude that our property P is true for all integers that are at least our starting point and going up. So one proposition that we might consider to apply weak induction would be this proposition, P of n, which is defined as the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So let's see how we can prove that using weak induction. So why is it true that that sum from I equals 1 to n of I is equal to n times n plus 1 over 2? In order to prove it with weak induction, we have two parts. We need to prove a base case. And the base case is usually pretty simple. In this case, it's very simple. We just show that the sum from I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2. And that's clear because both sides are equal to 1. Once we prove the base case, all we have to do is prove the inductive step. For the inductive step, we assume an inductive hypothesis. The inductive hypothesis is that our P, the proposition, is true up to some k. And in fact, for weak induction, we aren't even going to use the fact that it's true for any lesser k. We'll only assume that it's true at k, P of k. In our case here, for this problem, the proposition is that this sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So if we're saying that that is true at k, all we're saying is that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. So that's our inductive hypothesis. And we're going to try to use that inductive hypothesis to prove that the next step of the induction is true. In other words, in this case, for this problem, to prove that the sum from I equals 1 to k plus 1 of I is equal to k plus 1 times k plus 1 plus 1 all of that over 2. So in order to prove that, we can start with the sum on the left. We can start with the sum from I equals 1 to k plus 1 of I. We can write the sum taking the k plus 1 out as k plus 1 plus the sum from I equals 1 to k of I. And we can use our inductive hypothesis here to substitute for the sum. And we can write this as k plus 1 plus k times k plus 1 over 2. And then we can simplify this, writing the k plus 1 as 2k plus 2 over 2. And this gives us k plus 1 times k plus 1 plus 1 over 2. Here's another example of applying weak induction, and this is for another sum. So why is it true that the sum from I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1? So we'll prove a base case first. The base case is just showing that the sum from I equals 0 to 0 of 2 to the I is equal to 2 to the 0 plus 1 minus 1. And that's true because, again, both sides are equal to 1. For the inductive step, we'll again assume an inductive hypothesis. Here our inductive hypothesis is different. It's saying that the sum from I equals 0 to k of 2 to the I equals 2 to the k plus 1 minus 1. So we just took our proposition P of n, and P of n was that the sum from I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1. And we just wrote that with a k. When you're writing a weak induction proof, you can use any variables that you want. So I'm using a k here, but you can use a j or an I or whatever you feel like. Maybe an I wouldn't work that well here since we have an I in the sum. So we want to use our inductive hypothesis in the third bullet to prove the next step of our induction. In other words, to prove that the sum from I equals 0 to k plus 1 of 2 to the I equals 2 to the k plus 2 minus 1. So we'll start with that sum on the left, the sum from I equals 0 to k plus 1 of 2 to the I. We'll do something kind of similar to what we did in the last problem. We'll pull out the k plus 1 term. So in other words, we'll pull out the 2 to the k plus 1. And then we get that plus the sum from I equals 0 to k of 2 to the I. We can use our inductive hypothesis here. We get 2 to the k plus 1 plus the quantity 2 to the k plus 1 minus 1. And we can simplify this to 2 to the k plus 2 minus 1. So that completes our weak induction proof. Let's look at one more example before we move on. So another sum, and this time we're doing the sum from I equals 1 to n of I squared. And we want to prove that this sum is equal to n times n plus 1 times 2n plus 1 over 6. So it's going to be very similar to the two problems that we just did. First, we'll prove a base case. Base case is just the sum from I equals 1 to 1 of I squared. And this is equal to 1. And 1 is equal to 1 times 1 plus 1 times the quantity 2 times 1 plus 1 all over 6. So since those quantities are all equal to 1, we have the base case. Now, to prove the inductive step, again, this one is really similar to the previous ones. We'll suppose that the sum from I equals 1 to k of I squared is equal to k times k plus 1 times 2k plus 1 over 6. And we want to use that inductive hypothesis to prove the next step is true. In other words, to prove that the sum from I equals 1 to k plus 1 of I squared is equal to k plus 1 times k plus 1 times the quantity 2 times quantity k plus 1, and then that plus 1, all over 6. So it's the same thing that we have in the previous line, but we're replacing the k's with the k plus 1. So we're trying to show that p of k implies p of k plus 1, where our p of n proposition is that the sum from I equals 1 to n of I squared equals n times n plus 1 times 2n plus 1 over 6. And in order to prove this, we're going to use kind of a similar method that we just used in the previous problems. We're going to start with that sum on the left, the sum from I equals 1 to k plus 1 of I squared. We'll pull out the k plus 1 term, which is the k plus 1 squared, and then we can write it as that term plus sum from I equals 1 to k of I squared. We use our inductive hypothesis. We get k plus 1 squared plus k times k plus 1 times 2k plus 1 over 6. And then we can write that k plus 1 squared as k plus 1 times 6k plus 6 over 6. And then we can combine the two fractions and we get k plus 1 times, and then the quantity 6k plus 6 plus 2k squared plus k, and then all of that over 6. And it simplifies to give us k plus 1 times k plus 2 times 2k plus 3 over 6, because the 2k squared plus 7k plus 6 is k plus 2 times 2k plus 3. Now, the first and third examples that we saw, so showing that the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6, and also showing that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So both of those proofs were pretty straightforward since we already knew what we were trying to prove. It would be more difficult though if we didn't know what we were trying to prove and we were just trying to evaluate the sum. So for example, here's one like that. How can we calculate the sum from I equals 1 to n of I cubed? So we're going to discuss a method, and it will work for any finite sums of polynomials like this. So we look at the sum, and we look at the polynomial that we have inside the sum that we're summing over. In this case, we have an I cubed. So as a polynomial, like we have polynomial p of x, that would be the polynomial p of x equals x cubed. We look at what is the degree of that polynomial. If that polynomial has degree d, the sum will have degree d plus 1. So in this case, p of x equals x cubed, that has degree 3. So we're going to claim that the sum from I equals 1 to n of I cubed is going to have degree 4 as a polynomial in n. So we're going to write the sum from I equals 1 to n of I cubed. Since we're claiming that it has degree 4, we can write it as an to the 4th plus bn cubed plus cn squared plus dn plus e, where a, b, c, d, and e are all real numbers. And now we're going to try to solve for a, b, c, d, and e in order to make this true. And once we solve for the a, b, c, d, and e, we will prove that it is true. So far, for for this problem, we haven't proved anything yet. We haven't done any induction. All we're doing so far is looking at a technique that will get us the answer that we're looking for. And once we get that answer, then we can do the induction. So like I said, we're going to solve for A, B, C, D, and E. We have 5 unknown variables. That means we want to come up with a system of 5 equations. And we're going to have linear equations. In order to come up with those equations, all we have to do is evaluate the sum from I equals 1 to n of I cubed for 5 distinct values of n. So we can evaluate it at n equals 1, n equals 2, n equals 3, and n equals 4. And we can say that it's 0 at n equals 0. So first, the n equals 0, if we're saying that that sum from I equals 1 to n of I cubed is equal to an to the 4th plus bn cubed plus cn squared plus dn plus e, and we're saying at n equals 0 that that sum is 0, and that tells us that when we plug in 0 into an to the 4th plus cn cubed plus bn cubed plus cn squared plus dn plus e, that has to give us 0. So that tells us that a times 0 to the 4th plus b times 0 cubed plus c times 0 squared plus d times 0 plus e equals 0. We can also plug in 1 into that polynomial in n, the polynomial an to the 4th plus bn cubed plus cn squared plus dn plus e. When we plug in 1, we get a times 1 to the 4th plus b times 1 cubed plus c times 1 squared plus d times 1 plus e. We want that to be equal to the sum from I equals 1 to 1 of I cubed. And that gives us 1 cubed. That's the only element in the sum, which is equal to 1. Now, the next line right here, we plug in 2. And this gives us a times 2 to the 4th plus b times 2 cubed plus c times 2 squared plus d times 2 plus e, and this equals 1 cubed plus 2 cubed. So we want that to equal our sum from I equals 1 to n of I cubed with n equals 2. So 1 cubed plus 2 cubed gives us 9. And we'll plug in 3, similarly to how we plugged in 0, 1, and 2. And we want a times 3 to the 4th plus b times 3 cubed plus c times 3 squared plus d times 3 plus e. We want that to equal our sum from I equals 1 to n of I cubed for n equals 3. And that gives us 1 cubed plus 2 cubed plus 3 cubed, and this gives us 36. And we have only one more sum, which is what we get by plugging in n equals 4. So we want a times 4 to the 4th plus b times 4 cubed plus c times 4 squared plus d times 4 plus e to equal our sum up to n equals 4. This gives us 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, which is just 100. So we have a system with 5 equations here. Now we can turn the system of 5 equations into a matrix equation. So this matrix equation, on the right side, it has a 5 by 1 matrix, which we can also consider as a column vector. That column vector is 0, 1, 9, 36, 100. We got that from taking the right sides of all of the equations in our 5x5 system of equations. On the left side of our matrix equation, we have a 5x5 matrix. Each of its rows is obtained by using one of our equations from above. The first row is from the first equation. It's the coefficients of the A, B, C, D, and E. So we get 0, 0, 0, 0, 1. We look at the coefficients of the A, B, C, D, and E in the second equation, which gives us 1, 1, 1, 1, 1. That's the second row of the matrix. The third equation, the coefficients of A, B, C, D, and E, are 16, 8, 4, 2, and 1. And that gives us the third row of the matrix. And similarly, the fourth row of the matrix, we get 81, 27, 9, 3, and 1 from the coefficients of the A, B, C, D, and E in the fourth equation. And finally, the fifth row of the matrix is just the coefficients of the A, B, C, D, and E in the fifth equation, which is 256, 64, 16, 4, and 1. And this 5x5 matrix times the column vector A, B, C, D, E needs to give us 0, 1, 9, 36, 100. I'll note also that the sum that we're looking at, sum from I equals 1 to n of I cubed, this is the same as the sum from I equals 0 to n of I cubed for any n greater than or equal to 1. So if we want to know the sum for any n greater than or equal to 1, it's fine for us to be using the first equation for 0. So we have this matrix equation. And this matrix equation, we have an invertible 5x5 matrix on the left. So we will multiply by its inverse on both sides of the equation, but on the left side of both sides of the equation. When we multiply by the inverse, it cancels with the 5x5 matrix on the left side of the equation. So we're left with the column vector A, B, C, D, E. And this is equal to the inverse of the 5x5 matrix times the column vector 0, 1, 9, 36, 100. And you can simplify that with whatever you like to use to calculate matrix inverses, maybe a calculator, a Wolfram Alpha, something like that. And that will leave you with 1/4, 1/2, 1/4, 0, 0, the 5x1 matrix. So that just told us that the sum from I equals 1 to n of I cubed, assuming that it's a polynomial in n of degree 4, it's going to be the polynomial 1/4 n to the 4th plus 1/2 n cubed plus 1/4 n squared. And we can write that as n squared times n plus 1 squared over 4. The thing is, we didn't prove that it's true yet. We only showed that if it is a polynomial of degree 4 in n, that's what it has to be, but we didn't show that that actually works. So we need to prove that it's actually true that this sum from I equals 1 to n of I cubed is equal to n squared times n plus 1 squared over 4. So in order to prove that, that's where the induction will come in. So we found what the sum should be, and now in order to prove that the answer is right, we're going to use weak induction. So to use weak induction, it'll be like this, like the examples we did earlier. So we'll do a base case, and that will be real similar to what we did for the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So the method we do here for the induction, it'll be almost the same as that, just with a higher power of I. So here's our base case. The sum from I equals 1 to 1 of I cubed is equal to 1 squared times 1 plus 1 squared over 4. That's true because both sides are just 1. And then the inductive step. We'll suppose that the sum from I equals 1 to k of I cubed equals k squared times k plus 1 squared over 4. In other words, we're supposing that p of k is true. That'll be our inductive hypothesis. And we're trying to prove that p of k plus 1 is true. And p of k plus 1 in this case is saying that the sum from I equals 1 to k plus 1 of I cubed is equal to k plus 1 squared times k plus 1 squared, all of that over 4. So we'll proceed real similarly to how we did in those previous examples. We'll start with the sum on the left, from I equals 1 to k plus 1 of I cubed. We'll pull out the k plus 1 term, which is k plus 1 cubed here, and then we're adding that to the sum from I equals 1 to k of I cubed. And then we can use our inductive hypothesis. So we replace the sum with k squared times k plus 1 squared over 4. And when we add the k plus 1 cubed to it, we can write the k plus 1 cubed as k plus 1 squared times 4k plus 4 over 4. And this gives us, when we combine them, k plus 1 squared times k squared plus 4k plus 4 over 4. And that simplifies to k plus 1 squared times k plus 2 squared over 4. So here's a problem for you. Simplify the sum from I equals 1 to n of 2i to the 4th minus 3i squared plus 5i minus 7, and prove that your answer is correct. So earlier in this video, we saw that the sum from I equals 0 to n of 2 to the I is equal to 2 to the n plus 1 minus 1. And we're going to see how to generalize this now. So suppose that we have some real number r. Suppose further that r is not equal to 1. Then I claim that the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 divided by 1 minus r. Why is this true? Well, we can do some multiplication and we'll see that there's massive cancellation. So let's look at why this is true. We're going to multiply 1 minus r, and we're multiplying that times this sum, which is a sum from I equals 0 to n of r to the I. And when we write this sum, instead of using sum notation, we can just write it out. So we get r to the 0, which is 1, plus r to the 1, which is r, plus r squared, plus r cubed. I'll write a couple more terms, and then we'll do a dot, 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 plus r to the 4th, and then let's have at the end of that an r to the n. Okay, so we have 1 minus r times this finite sum. Now, when we use the distributive property, we'll get 1 minus r times 1 plus 1 minus r times r plus 1 minus r times r squared plus 1 minus r times r cubed plus 1 minus r times r to the 4th. I'll just do a dot, dot, dot after this one, I guess. And then plus 1 minus r times r to the n. And now we can simplify further. So we get a 1 minus r plus r minus r squared plus r squared minus r cubed plus r cubed minus r to the 4th plus r to the 4th minus r to the 5th plus dot, dot, dot plus r to the n minus r to the n plus 1. We can see that everything cancels except for the first term and the last term. So we're left with only this 1 here and this minus r to the n plus 1 over here. So we can divide both sides by 1 minus r. Since we see that 1 minus r times the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1. So when we divide both sides by 1 minus r, and that's fine to do because r is not equal to 1, that's what gives us that the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 divided by 1 minus r. So we were able to derive a generalization of the sum that we found for these powers of 2. Another way to prove this generalization is to use weak induction. When we use weak induction to prove this, we start with the base case. The base case is for n equals 0. So we show the sum from I equals 0 to 0 of r to the I is equal to 1 minus r to the 1 over 1 minus r. And r to the 1 is equal to r to the 0 plus 1. And the reason why this is true is because both of those sides are equal to 1. And that's true because r is not equal to 1. Now for the inductive step. Our inductive hypothesis here will be that the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 over 1 minus r. So notice that I didn't use a k here, I used an n. This is fine. You can use any variable that you want. So it's fine to use an n in your inductive hypothesis variable. It's fine to use an m, an x, whatever you feel like. Now, in order to use that inductive hypothesis to prove the next step of the induction, all we have to do is take our sum for the next step, which is sum from I equals 0 to n plus 1 of r to the I, and we pull out our n plus 1 term, which is r to the n plus 1, and we use our inductive hypothesis, and we see that this sum from I equals 0 to n plus 1 of r to the I is equal, by inductive hypothesis, to r to the n plus 1 plus the quantity 1 minus r to the n plus 1 over 1 minus r. So in that step, for that equality, we pulled out the r to the n plus 1 and we used the inductive hypothesis, both in the same step. Now, we can write that r to the n plus 1 with a denominator of 1 minus r. When we have a denominator of 1 minus r, we get in the numerator an r to the n plus 1 minus r to the n plus 2. And when we multiply that to the 1 minus r to the n plus 1 over 1 minus r, we cancel out the r to the n plus 1s, and that gives us a numerator of 1 minus r to the n plus 2 and the denominator of 1 minus r. Here's a problem for you. Simplify this sum from I equals 7 to 2n plus 11 of 3 to the I minus 5. And prove your answer. So, on the previous slide, we saw multiple ways that you can prove that the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 over 1 minus r, as long as r is not equal to 1. Suppose that the absolute value of r is less than 1. In that case, you can observe that the quantity r to the n plus 1, which is the quantity that we're seeing in the numerator, that quantity goes to 0 as n goes to infinity. Thus, we can conclude that the sum from I equals 0 to infinity of r to the I is equal to 1 over 1 minus r, as long as the absolute value of r is less than 1. Here's a problem for you to think about. Simplify the sum from I equals 7 to infinity of 2/3 to the I minus 5, and prove that your answer is correct. So, before we finish this video, let's look at another type of infinite series. The question that we'll focus on is to determine the exact value of the sum from I equals 1 to infinity of I over 2 to the I. We can see that this sum converges by using, for example, the ratio test. There's multiple ways to observe that this converges, but the ratio test is perfectly fine. Now, we can actually see that this sum can be rewritten as a sum of sums that we know how to evaluate. Let's look at why this is true, that we can rewrite this sum this way. So the sum at the top, the sum from I equals 1 to infinity of I over 2 to the I. I'm going to write that sum in this open space as 1 over 2 to the 1 plus 2 over 2 to the 2 plus 3 over 2 to the 3 plus 4 over 2 to the 4 plus 5 over 2 to the 5, and so on. We'll do dot, dot, dot after that. And then we're going to write that sum in a different way, but it's going to be clear from how we wrote this. So we can say that this is equal to this sum, 1 over 2 to the 1. And I'm going to take that 2 over 2 to the 2. I'm going to split it up into 1 over 2 to the 2's. So I'm going to write it as 1 plus 1, and that over 2 to the 2. And then this 3 over 2 to the 3, similarly, I'll write that as 1 plus 1 plus 1. And then finally, this 4 will do a 1 plus 1 plus 1 plus 1. And then we'll do a dot, dot, dot after that. Okay, now we can rewrite this in a way that's going to be clear that it's equal to the sum of sums that we see in the third bullet. So we're going to write the 1 over 2 to the 1 the same as we did before. Now we have a 1 plus 1 over 2 to the 2 right here. So we're going to write one of those 1 over 2 to the 2's right here. And then we'll write the other one right here. Now up here, we have a 1 plus 1 plus 1 over 2 to the 3. So we'll write one of them right here. 1 over 2 to the 3. Another one right here, 1 over 2 to the 3. And then down here, the last one, 1 over 2 to the 3. And now the 1 plus 1 plus 1 plus 1 over 2 to the 4th, we'll write 1 over 2 to the 4th right here. 1 over 2 to the 4th right here. 1 over 2 to the 4th right here. and then we get a 1 over 2 to the fourth down here. And it keeps on going like this. So we can get our 1 over 2 to the fifths. And it just goes diagonally like this. So keeps on going. And we look at that first line of the sum. That first line is 1 over 2 to the 1 plus 1 over 2 to the 2 plus 1 over 2 to the 3 plus 1 over 2 to the 4, and so on. And that's equal to the sum from j equals 1 to infinity of 1 over 2 to the j. The second line is 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth plus 1 over 2 to the fifth, and so on. This is the same as the sum from j equals 2 to infinity of 1 over 2 to the j. The third line is 1 over 2 cubed plus 1 over 2 to the fourth plus 1 over 2 to the fifth plus 1 over 2 to the sixth, and so on, going forever. That's the same as the sum from j equals 3 to infinity of 1 over 2 to the j. And it continues like this for each of the lines. So the jth line is equal to the sum from, well, instead of saying the jth line, let me say the ith line. The ith line of this sum that we see, this diagonal sum at the bottom that I just put in a box. So we have line 1, line 2, line 3, line 4, and so on. So the ith line of that is equal to the sum from j equals I to infinity of 1 over 2 to the j. So when we add up all the lines of this sum, we get the sum from I equals 1 to infinity of the sum from j equals 1 to, from j equals I to infinity of 1 over 2 to the j. So our outer sum runs from I equals 1 to infinity. Our inner sum runs from j equals I to infinity. Because again, the ith line in our sum at the bottom is the sum from j equals I to infinity of 1 over 2 to the j. So that's the reason why we're able to rewrite the sum from I equals 1 to infinity of I over 2 to the I as the sum from I equals 1 to infinity of the sum from j equals I to infinity of 1 over 2 to the j. So I'm going to clear that, and then we'll see how we can finish off this nested sum and get an exact value. So when we evaluate the nested sum, we can see that the inner sums, we already know what those are. So the inner sum from j equals I to infinity of 1 over 2 to the j is equal to 1 over 2 to the I times the sum j equals 0 to infinity of 1 over 2 to the j. So we get 1 over 2 to the I times 1 divided by 1 minus 1/2. And that gives us 1 over 2 to the I minus 1 as the value for the sum j equals I to infinity of 1 over 2 to the j. And we're summing that from I equals 1 to infinity. So we're taking the sum from I equals 1 to infinity of 1 over 2 to the I minus 1. And that's the same as 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. So we get 1 over 1 minus 1/2, and that's equal to 2. So that's the value of the sum, I equals 1 to infinity of I over 2 to the I. And we can use similar methods for other sums where we have a polynomial in I over some power of I as the term that we're summing over. So for example, here's a problem you can think about. Simplify this sum from I equals 1 to infinity of 2I minus 3 divided by 5 to the I, and prove that your answer is correct. And here's a slightly more interesting one you can think about. And again, similar method works for this one. Simplify the sum from I equals 1 to infinity of I squared over 7 to the I. And again, prove that your answer is correct. Thanks for watching.